Welcome to Quantum Mechanics. My name is Brant Carlson. Since this is the first lecture on quantum mechanics, we ought to have some sort of an introduction. And what I want to do to introduce quantum mechanics is to explain, first of all, why it's necessary, and second of all, to put it in historical context to, I'll show one of the most famous photographs in all of physics that really gives you a feel for the brain power that went into the construction of this theory. And hopefully we'll put it in some historical context as well, so you can understand where it fits in the broader philosophy of science. But the main goal of this lecture is about the need for quantum mechanics, which I really ought to just have called, Why Do We Need Quantum Mechanics? This subject has a reputation for being a little bit annoying, so why do we bother with it? Well, first off, for some historical context, imagine yourself back in 1900. Turn of the century, science has really advanced a lot. We have electricity, we have all this fabulous stuff that electricity can do, and even almost 100 years before that, physicists thought they had things figured out. There's a famous quote from Laplace: "Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective position of the beings which compose it, nothing would be uncertain, and the future, as the past, would be present to its eyes." Now, maybe you think intelligence which can comprehend all the forces of nature is a bit of a stretch. And maybe such a being which can know all the respective positions of everything in the universe is a bit of a stretch as well. But the feeling at the time was that if you could do that, you would know everything. If you had perfect knowledge of the present, you could predict the future. And of course you can infer what happened in the past. And everything is connected by one unbroken chain of causality. Now, in 1903, Albert Michelson, another famous quote from that time period, said, "The more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the sixth place of decimals." Now, this sounds rather audacious. This is 1903, and he thought that the only thing that we had left to nail down was the part in a million level precision. Well, to be fair to him, he wasn't talking about never discovering new fundamental laws of physics. He was talking about really astonishing discoveries like the discovery of Uranus on the basis of orbital perturbations of Neptune. Never having seen the planet Uranus before, they figured out that it had to exist just by looking at things that they had seen. That's pretty impressive. And Michelson was really onto something. Precision measurements are really, really useful, especially today. But back in 1903, it wasn't quite so simple, and Michelson probably regretted that remark for the rest of his life. The attitude that I want you guys to take when you approach quantum mechanics, though, is not this sort of 1900s notion that everything is predicted. It comes from Shakespeare. Horatio says, "Oh, day and night, but this is wondrous strange," to which Hamlet replies, one of the most famous lines in all of Shakespeare, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." So that's the attitude I want you guys to take when you approach quantum mechanics. It is wondrous strange, and we should give it welcome. There are some things in quantum mechanics that are deeply non-intuitive, but if you approach them with an open mind, quantum mechanics is a fascinating subject, and there's a lot of really fun stuff that goes on. Now, to move on to the necessity for quantum mechanics, there were some dark clouds on the horizon, even at the early 20th century. Michelson wasn't quite having a big enough picture in his mind when he said that everything was down to the sixth place of decimals. The dark clouds on the horizon, at least according to Kelvin here, were a couple of unexplainable experiments. One, the black body spectrum. Now, a black body you can just think of as a hot object. And a hot object, like, for example, the coils on an electrical stove, when they get hot, will glow. And the question is, what color do they glow? Do they glow red? Do they glow blue? What is the distribution of radiation that is emitted by a hot object? Another difficult to explain experiment is the photoelectric effect. If you have some light and it strikes a material, electrons will be ejected from the surface. And as we'll discuss in a minute, the properties of this experiment do not fit what we think we know about, or at least what physicists thought they knew about the physics of light and the physics of electrons at the turn of the 20th century. The final difficult experiment to explain is bright line spectra. For example, if I have a flame coming from, say, a Bunsen burner, and I put a chunk of something, perhaps sodium, in that flame, it will emit a very particular set of frequencies that looks absolutely nothing like a black body. We'll talk about all of these experiments in general, or in a little bit more detail in a minute or two, but just looking at these experiments now, these are all experiments that are very difficult to explain, knowing what we knew at the turn of the 20th century about classical physics. And they're also experiments that involve light and matter. So we're really getting down to the details of what stuff is really made of and how it interacts with the things around it. These are some pretty fundamental notions, and that's where quantum mechanics really got its start. So let's pick apart these experiments in a little more detail. The black-body spectrum, as I mentioned, you can think of as the light that's emitted just by a hot object. And while hot objects have some temperature associated with them, let's call that T. The plot here on the right is showing very qualitatively, I'll just call it the intensity of the light emitted as a function of the wavelength of that light. So short wavelengths, high energy, long wavelengths, low energy. Now if you look at T equals 3500 Kelvin curve here, it has a long tail to long wavelengths, and it cuts off pretty quickly as you go to short wavelengths. So it doesn't emit very much high energy light. Whereas if you have a much hotter object, 5500 Kelvin, it emits a lot more high energy light. The red curve here is much higher than the black curve. Now if you try to explain this, knowing what early 20th century physicists knew about radiation and about electrons and about atoms and how they could possibly emit light, you get a prediction. And it works wonderfully well up until about here, at which point it blows up to infinity. Infinities are bad in physics. This is the Rayleigh-Jeans law, and it works wonderfully well for long wavelengths, but does not work at all for short wavelengths. That's called the ultraviolet catastrophe, if you've heard that term. On the other end of things, if you look at what happens down here, well, it's not so much a prediction but an observation, but there's a nice formula that fits here. So on one side, we have a prediction that works well on one end but doesn't work on the other. And on the other hand, we have a sort of empirical formula called Wien's law that works really well at the short wavelengths, but, well, also blows up to infinity at the long wavelengths. Both of these blowing up things are a problem. And the question is, how do you get something that explains both of them? This is the essence of the black-body spectrum and how it was difficult to interpret in the context of classical physics. The next experiment I mentioned is the photoelectric effect. This is sort of the opposite problem. It's not how a material emits light, it's how light interacts with the material. So you have light coming in, and the experiment is usually done like this. You have your chunk of material, typically a metal, and when light hits it, electrons are ejected from the surface, hence the electric part of the photoelectric effect. And you do all this in a vacuum, and the electrons are then allowed to go across a gap to some other material, another chunk of metal, where they strike this metal. And the experiment is usually done like this. You connect it up to a battery. So you have your material on one side and your material on the other, and you have light hitting one of these materials and ejecting electrons. And you tune the voltage on this battery such that your electrons, when they're ejected, never quite make it. So the electric field produced by this voltage is opposing the motion of the electrons. When that voltage is just high enough to stop the motion of the electrons, keep them from completely making it all the way across, we'll call that the stopping voltage. Now, it turns out that what classical E&M predicts, as I mentioned, doesn't match what actually happens in reality. But let's think about what does classical E&M predict here. Well, classical electricity and magnetism says that electromagnetic waves here have electric fields and magnetic fields associated with them, and these are propagating waves. If I increase the intensity of the electromagnetic wave, that means the magnitude of the electric field involved in the electromagnetic wave is going to increase. And if I'm an electron sitting in that electric field, the energy I acquire is going to increase. That means V stop is going to increase, because I'll have to have more voltage to stop a higher energy electron, as would be produced by a higher intensity beam of light. The other parameter of this incoming light is its frequency. So we can think about varying the frequency. If I increase the frequency, I have more intense light. Now, that doesn't say anything about the string, if I increase the frequency, I don't necessarily have more intense light. The electric field magnitude is going to be the same, which means the energy and the stopping voltage will also be the same. Now, it turns out what actually happens in reality does not match this at all. In reality, when the intensity increases, the energy, which I should really write as V stop, the stopping voltage necessary, doesn't change. And when I increase the frequency, the voltage necessary to stop those electrons increases. So this is sort of exactly the opposite. What's going on here? That's the puzzle in explaining the photoelectric effect. Just to briefly check your understanding, consider these plots of stopping voltage as a function of the parameters of the incident light, and check off which you think shows the classical prediction for the photoelectric effect. The third experiment that I mentioned is bright line spectra. And as I mentioned, this is what happens if you take a flame or some other means of heating a material, like the bar of sodium I mentioned earlier. This will emit light, and in this case, the spectrum of light from red to blue of sodium looks like this. Actually, I'm sorry, that's not sodium, that's mercury. These are four different elements: hydrogen, mercury, neon, and xenon. And instead of getting a broad, continuous distribution, like you would from a black body, under these circumstances where you're talking about gases, you get these very bright regions. It's the spectrum, instead of looking like a smooth curve like this, looks like spikes. Those bright lines are extraordinarily difficult to explain with classical physics, and this is really the straw that broke the camel's back, broke classical physics' back, that really kicked off quantum mechanics. How do you explain this? This is that famous photograph that I mentioned. This is really the group of people who first built quantum mechanics. Now, I mentioned three key experiments. The black body spectrum. This guy figured that out. This is Planck. The photoelectric effect. This guy, who I hope needs no introduction, this is Einstein, figured that out. This is the paper that won Einstein the Nobel Prize. And as far as the bright line spectra of atoms, it took a much longer time to figure out how all of that fit together. And it took a much larger group of people. But they all happen to be present in this photograph. There's this guy, and these two guys, and this guy. This photograph is famous because these guys worked out quantum mechanics. But that's not the only, these aren't the only famous people in this photograph. You know this lady as well. This is Marie Curie. This is Lorentz, which if you studied special relativity, you know Einstein used the Lorentz transformations. Pretty much everyone in this photograph is a name that you know. I went through